a warning from the sky. 7 travelers are converging on the realm of the inner planets at almost the same season. 6 are comets from our own deep freeze. 1 is not from here at all. It is the 3rd confirmed interstellar object to visit the Sun. In late 2025, these bodies will thread paths that briefly overlap in time, if not in space, turning the solar system into a natural laboratory. The night sky will tell a fast-moving story of ice, dust, electric fields, and magnetic storms. Spacecraft will watch from many directions. Ground-based observers will see tails lengthen, fragment, and sometimes break away. For a few weeks in October and November, the sky will behave like a living diagram of heliophysics. And at the center of attention is an alien visitor that astronomers call 3I/ATLAS, a rare interstellar comet making a swift passage through the plane of the planets. It is not a threat to Earth. It is an opportunity to learn. Across this same window of time, 2 homegrown comets rise to prominence. The first is C 2025 R2 SWAN, a newly identified object that came to solar perihelion in mid-September and now sweeps northward, approaching our planet to a distance of roughly 1/4 of an astronomical unit near the 3rd week of October. The second is C 2025 A6 Lemmon, a long-period comet that will likely climb to naked eye threshold brightness under dark skies and then reach its own closest point to the Sun in early November. Together with 3 additional inbound comets and the interstellar traveler, they complete the cast of 7. A sustained observing campaign led by professional and amateur instruments will follow their orbits, brightness changes, and the behavior of their dust and plasma tails as the solar wind varies. Begin with the signal from space agencies. The National Aeronautics and Space Administration has confirmed that 3I/ATLAS will pass closest to the Sun in late October at roughly 1 4/10 astronomical units, well outside Earth's orbit, with a closest approach to our planet in mid-December at about 1 8/10 astronomical units. The European Space Agency and collaborating teams expect orbital spacecraft near Mars and other platforms to attempt observations because the interstellar comet will be much better placed for robots than for Earth-bound telescopes during its solar conjunction. The approach geometry hides the comet in evening twilight for most observers on Earth near its decisive passage by the Sun. A simple map of the players clarifies what is coming. The interstellar comet 3I/ATLAS is the headline object. It is categorized as a hyperbolic interstellar intruder and will be faint from our point of view, because it never comes close to Earth. The homegrown comets likely to matter for visual observers include C 2025 A6 Lemmon, predicted to be visible to the unaided eye at around 4th magnitude in late October and early November under dark skies, and C 2025 R2 SWAN, now moving away from the Sun and closing toward Earth to roughly 1/4 of an astronomical unit near the 3rd week of October. Add C 2025 K1 Atlas, which reaches perihelion in early October with an orbit that brings it close to the Sun and therefore carries a non-trivial risk of fragmentation, plus the periodic comets 210 P. Christensen and 24 P. Shalmaser, both likely binocular objects, and the more distant long-period Comet C 2024 E1 Virchow. That roster provides 6 comets from the home system, plus the interstellar visitor, to make the 7 bodies that motivate this surge of attention. Consider the physics that makes comets such precise sensors of the Sun. A comet is not a dirty snowball in any literal sense. It is a loosely bound mixture of ices, trapped gases, and dust grains that release material as sunlight warms the surface and as thermal waves penetrate. Outgassing builds a coma, the spherical envelope where gas collides, ionizes, and interacts with sunlight. 2 large-scale tails then form at once. The dust tail curves away along the orbit, shaped by solar radiation pressure that pushes small grains more strongly than large grains. The plasma tail points almost directly away from the Sun along the prevailing solar wind. The classic description of dust tail geometry uses synchrone and syndine curves, a framework that links particle size and time of release to the shape of the visible tail. Those curves, worked out in the 20th century, will again help decode photographs of SWAN and Lemon this season. Plasma tails carry an additional drama. They can disconnect when a coronal mass ejection sweeps past a comet. The interplanetary magnetic field can suddenly rotate and reconnect. That change in the magnetic field severs the plasma tail. The old tail drifts away. A new tail begins growing almost immediately. The stereo spacecraft recorded a spectacular case on Comet Enki in April 2007, when a coronal mass ejection ripped away the tail in full view. Laboratory and computational studies now model the same process, showing that a strong rotation of the magnetic field embedded in the solar wind can reproduce the behavior seen in space. If solar storms remain active as the new comets brighten, tail disconnection events are a real possibility for photographers and heliophysicists alike. Now focus on the alien. 3 I/Atlas, also catalogued as C 2025 N1 Atlas, is only the 3rd interstellar object confirmed to enter the solar system. It is on a steeply retrograde path that lies close to the plane of the planets. The interstellar visitor will pass near Mars in early October, then sweep to perihelion in the final days of October, and later pass far from Earth in mid-December. Because the solar elongation is small from early October through early November, ground-based observers will see the comet only in bright twilight or not at all during the key days. Space-based platforms, however, have a much better view. Teams working with missions at Mars and with solar observing spacecraft are preparing to exploit that advantage, hoping to capture changes in coma chemistry and tail structure as the interstellar ice warms. Interstellar chemistry is the most provocative question. The previous interstellar Comet I Borisov carried an unusually high fraction of carbon monoxide relative to water compared with most solar system comets observed at similar distances from the Sun. That composition pointed to formation in an extremely cold region beyond the carbon monoxide ice line in its birth system. If 3 I/Atlas shows a different blend of carbon monoxide, carbon dioxide, water, and nitriles, it will broaden our understanding of planet-forming disks across the galaxy. Even color matters. Several recent images show 3 I/ATLAS with a greenish hue associated with emission from diatomic carbon and cyanide in the coma. That color is transient and not intrinsic to the nucleus. It records the chemistry of gas in sunlight. 3I/Atlas will not be a showpiece for the unaided eye. It remains faint because the geometry keeps it far away. The interest for ground observers comes from the physics it will test and from the spacecraft that may watch it from better vantage points. The interest for heliophysics comes from timing. The interstellar comet will be immersed in a changing solar wind during an active part of the solar cycle. Researchers will search for fluctuations in ion tail direction, for signs of dust outbursts, and for possible X-ray signatures from charge exchange as heavy ions in the solar wind capture electrons from neutral gas in the coma. That X-ray glow, discovered in the 1990s and now studied with space telescopes, turns comets into remote monitors of solar wind composition. Return now to the nearer targets. Lemon is the practical star of this season. It was discovered at Mount Lemon in early January and has outperformed early brightness estimates. Conservative forecasts place its peak brightness in the range of 5th to 4th magnitude, which means it could be visible to dark adapted eyes. Optimistic curves have suggested a bit brighter, while cautious models hold closer to 7th magnitude at peak. All comet brightness forecasts are provisional. Outbursts, dust to gas ratios, and geometry matter. What is not provisional is its calendar. Lemon should be best placed for northern observers in the second half of October as it moves into the evening sky and climbs in declination. Perihelion follows in early November at a distance of a little more than 1/2 of an astronomical unit from the Sun. The light curve of a comet is not a simple line. A rule of thumb used by observers expresses the apparent magnitude as a constant for the nucleus plus 5 times the logarithm of the distance from Earth plus a factor times the logarithm of the distance from the Sun. The factor depends on activity. Dust-rich comets often brighten faster with decreasing solar distance than gas-poor comets. For Lemon, the rapid brightening after solar conjunction suggests that new active areas opened as sunlight penetrated to volatile, rich layers. If jets begin to dominate, the spin of the nucleus can modulate the light curve as the geometry of those jets with respect to the Sun and Earth changes. Spacecraft at Comet 67 P Churyumov-Gerasimenko demonstrated that outgassing torques can measurably alter a nucleus rotation period within a single apparition. Expect measurable short-term wiggles as Lemon approaches the Sun, even if the long-term trend remains steady. Lemon's appearance will change as dust production grows. The dust tail will broaden and curve. In longer exposures, a faint third component can sometimes appear in bright comets, a narrow tail of neutral sodium atoms. It was seen clearly in Comet Hale-Bopp and in other bright comets with specialized filters. Sodium emission reveals a delicate interaction between sunlight and dust grains, sometimes by direct sputtering of sodium off the grains, sometimes by grain-grain collisions that liberate atoms. Most comets this season will not be bright enough to show a sodium tail to the eye, but long focal length images with the right passband may capture it, and an audience attuned to this possibility will understand what they are seeing if a narrow additional tail appears. Now set a marker on the calendar for the near miss of October in the northern autumn sky. Around October 21 C 2025, R2 SWAN comes close to Earth at roughly 1/4 of an astronomical unit. Visibility will depend on latitude and local sky. Photographs already show a long tail measured against the background of Virgo and the bright star Spica. The discovery instrument that flags comets, named SWAN, is the Solar Wind Anisotropies Experiment on the Solar and Heliospheric Observatory. It maps ultraviolet emission from hydrogen across the entire sky. Comets are strong sources of hydrogen because solar ultraviolet light breaks water molecules in the coma into hydrogen and oxygen. That is why the instrument finds comets so effectively, and it is why a comet that shows up in SWAN images has usually begun vigorous outgassing. The timing of this close pass carries an additional twist. While SWAN climbs to its closest approach, the interstellar comet is near solar conjunction. 3I/Atlas will be effectively behind the Sun for Earth-based observers in late October, which is why spacecraft at other vantage points become so important. Mars orbiters may see it best near their own local evening or morning skyscapes. Solar imagers such as STEREO and facilities that watch the outer solar corona can include comets in their wide-angle fields as byproducts of coronal mass ejection observations. To observers on Earth, the practical result is that October brings one comet that is strongly placed for photographs and binoculars, and one comet that is physically pivotal but optically elusive. From a heliophysics perspective, the close Earth approach of SWAN is a gift. A comet tail is a tracer of the local solar wind. If a coronal mass ejection or a fast solar wind stream arrives during the week of closest approach, watch for kinks, steps, and rotations in the plasma tail. A full disconnection event is a distinct possibility, in which the ion tail detaches and drifts away while a new tail regrows from the coma. Such events happen quickly on human timescales. The stereo recordings of Encke showed that a dramatic change can unfold over minutes of time. Photographers taking time series images can capture the entire evolution in a single session. Observing tactics must match the geometry. For Lemon in late October, northern latitudes are favored as the comet moves into the evening sky. Look for it low in the west after sunset, then progressively higher as the days advance. A pair of 7x50 binoculars with a stable support will show the coma and a short tail under dark conditions. Small telescopes in the 10 to 15 centimeter class reveal structure in the inner coma and a longer dust tail as exposure time increases. For SWAN, near October 21, scan the region near the bright star Spica and the boundary of Virgo, then track northward night by night as the plume rotates away from the Sun. Use averted vision to bring out low surface brightness features and stack multiple short exposures rather than a single long exposure to balance tail length against sky glow. Finder charts published by experienced skywatching outlets provide reliable guides for both comets during this interval. Cameras can do more than record pretty scenes. Astrophotographers can extract physical information from images by measuring tail curvature and width. The dust tail's curve reflects the distribution of particle sizes because smaller grains feel more radiation pressure and therefore lag farther behind the nucleus. If you map the tail ridge line across several nights, you can see the shift from large grains near the nucleus to small grains farther out. The plasma tail's direction traces the magnetic field carried by the solar wind. If a kink travels down the tail, you are seeing a change in the local magnetic field orientation or speed. In sustained time series, an apparent ripple moving away from the nucleus may be a signature of a compression region in the solar wind, while a sudden break indicates a reconnection event. These qualitative patterns have been used for decades to infer space weather conditions from the ground, and they remain relevant tools in the age of spacecraft. At radio and X-ray wavelengths, comets tell different stories. Charge exchange between highly ionized atoms in the solar wind and neutral atoms in the coma produces soft X-rays. The intensity and spectrum of that emission diagnose the composition and speed of the solar wind at the comet's location. Coordinated campaigns with X-ray telescopes have used comets as remote monitors of solar activity. During the weeks of heightened visibility in October and November, observers will watch for signs that Lemon and SWAN can serve as such monitors if solar activity remains elevated. These detections are not for backyard equipment, but they influence the interpretation of images taken from the ground, because a strong X-ray signal usually accompanies a highly active plasma environment. Turn now to the other members of the swarm. C 2025 K1 Atlas reaches perihelion in early October at about 1/3 of an astronomical unit from the Sun. Comets that close to the Sun face intense heating. Some survive and brighten, others break apart. If K1 Atlas remains intact, it could become a small telescope object for weeks as it recedes, with its nearest approach to Earth in late November at a comfortable yet distant few tenths of an astronomical unit. Its evolution is worth monitoring precisely because marginal comets teach so much about tensile strength, volatile layering, and the influence of rotation on structural failure. 2 periodic comets extend the season into early next year. 210P Christensen reaches perihelion in November and may be accessible in binoculars depending on sky conditions. 24P Chalmaser brightens toward the turn of the year and will be well placed for morning observations in late December and early January. Neither is expected to be bright to the unaided eye, but both are reliable targets for testing techniques developed on Lemon and SWAN. A further long-period comet, C 2024 E1 Wierskos, is predicted to hover near the threshold of small telescope visibility in late autumn. Together, these objects create continuity as the interstellar comet exits the inner system and returns to the dark between the stars. Behind the observing is a deeper agenda. 3I/ATLAS gives planetary science a point on a new curve. The first interstellar visitor, 1I Oumuamua, confounded expectations with its lack of obvious outgassing and its extreme shape and rotation state. The second, 2I Borisov, behaved like a classic comet, but with an unusually high abundance of carbon monoxide, hinting at formation far from its parent star. The third gives us a chance to expand that sample. Whether its coma turns out to be rich in carbon monoxide and carbon dioxide, or whether it shows a more water-dominated chemistry, the answer will feed models of planet-forming disks that must explain a variety of outcomes beyond our own. The National Aeronautics and Space Administration and allied observatories will publish refined measurements of its composition, rotation, and dust production as the data flow in from telescopes and spacecraft. Leveraging spacecraft adds texture to this story. the Solar Wind Anisotropies instrument on the Solar and Heliospheric Observatory maps the sky in ultraviolet light at the Lyman alpha wavelength of hydrogen. It routinely flags new comets because the hydrogen cloud around an active comet glows vividly at that wavelength. The twin stereo spacecraft and their heliospheric imagers can track comets far from the Sun while simultaneously following coronal mass ejections through interplanetary space. The Parker Solar Probe senses dust impacts and the electric and magnetic fields of the inner heliosphere, providing context about the environment through which comet tails must flow. Together, these platforms turn a handful of comets into a multi-probe experiment in solar system plasma physics. What should observers expect to see with their own eyes? For Lemon in late October, think of a small condensed coma and a sharply defined dust tail, perhaps a few degrees long in long exposure images. Depending on sky quality, the tail should curve gently in the direction opposite the Sun. If a strong solar wind disturbance arrives, a narrow blue-toned plasma tail may develop and could show a kink or step for SWAN near closest approach. The dust tail may appear broader and more diffuse, with a longer linear plasma tail on deep images. In both cases, short focal length lenses can capture the large-scale scene, but modest telescopes will reveal more inner detail. The interstellar comet will likely remain a target for telescopes and specialized cameras rather than the unaided eye. Expect fine images from professional facilities and from experienced amateurs using tracking mounts and stacking techniques. The science value of these apparitions extends beyond images. Photometry across weeks can detect outbursts, rotational modulation, and the growth or decay of activity. If Lemon approaches the 4th magnitude, visual estimates by experienced observers can be compared with digital photometry from small telescopes to calibrate the effect of coma condensation on brightness estimates. Dust tail profiles can be matched with synchrone and syndyne models to infer grain sizes and ejection velocities. Plasma tail direction can be compared with solar wind measurements from spacecraft near Earth to infer differences between the local environment of the comet and conditions near our planet. Such comparisons help validate models that translate heliospheric images into space weather forecasts. The comets also remind us that gravity is not the only force that matters for small bodies. Outgassing torques nudge rotation states. Patches of activity can switch on and off as the Sun's heat wave penetrates or as the subsolar point migrates across a rotating nucleus. Jets can precess, intensify, and fade as slopes and fissures receive sunlight. At Comet 67P, the Rosetta mission watched a nucleus speed up and later slow down as gas production surged and then declined. Similar processes act on every active comet. In extreme cases, fast rotation combined with internal weaknesses leads to fragmentation. K1 Atlas is a candidate to watch for that outcome if it experiences intense heating near the Sun. There is also the possibility of meteor activity seeded by dust released weeks earlier. When Earth crosses a fresh dust sheet laid along a comet's orbit, radiant points can blossom near unexpected constellations. SWAN's orbit geometry includes an Earth crossing early in October. Any meteor response would depend on how much dust the comet actually released during and after its perihelion. That is not guaranteed, but forewarned observers can place low-light cameras on the sky and check for a subtle enhancement. Even a negative result adds to our understanding of dust production rates and grain sizes. A final note on safety and technique. When seeking objects low in twilight, you must guard your eyes. Never sweep binoculars near the sun. Wait until the solar disk has set for the evening targets. Use a printed or digital finder chart from a reliable source so that you are not tempted to scan too close to the horizon while the sun is up. If you attempt daytime imaging near the sun using coronagraph data streams from space missions, remember that those instruments are designed with baffles and filters that your camera does not have. Visual observers should restrict themselves to after sunset and before sunrise windows unless they are working with solar-approved equipment. Finder charts and visibility guides for Lemon and SWAN are readily available from respected sky-watching services. As October advances, watch for 3 milestones. First, the week around October 21, when SWAN makes its closest approach to Earth at roughly 1/4 of an astronomical unit, and its tail geometry evolves rapidly against the background stars. Second, the final days of October, when 3 I/Atlas reaches perihelion but remains lost to most ground-based observers because of solar conjunction, even as spacecraft target it from deeper inside the system. Third, the first 10 days of November, when Lemon passes perihelion and could be at its best for northern observers just after dusk. Those 3 anchors define the shape of the season. Around them, the other comets supply continuity. This is the way to watch the surge as a coherent narrative. Begin by calibrating your expectations. Interstellar visitors are not guaranteed showpieces in visible light. They do their work by challenging models of composition and activity. Home system comets may surge or stall. A forecast of 4th magnitude can fail, or a quiet comet may explode into brief brilliance. Accept the volatility, then equip yourself. Use binoculars mounted on a simple parallelogram mount to relax your neck and keep the field steady. Learn your local light dome and work from a dark site for at least 1 hour after astronomical twilight ends. For photography, stack short exposures to reduce star trailing if you do not have a tracking mount. For a small tracking mount, experiment with a short telephoto lens to frame the comet against familiar star patterns so that the growth of the tail is obvious to the eye. Add a mindset for science. Log your observations with dates spelled out in full words and universal time when possible. Estimate the diameter of the coma in arc minutes by comparing it to known double star separations. Note the degree of condensation on a scale of 1 through 9 in words, from very diffuse to almost stellar, to help disentangle brightness changes caused by aperture effects. Keep a record of sky transparency and seeing. If you catch a tail, kink, or a disconnection, write down the time to the nearest minute of time and the angular distance of the feature from the nucleus. Those details turn a photograph into data that others can use. Tie your experience to the larger context. The solar wind anisotropies instrument on the Solar and Heliospheric Observatory will keep mapping hydrogen emission across the sky, sometimes revealing comets before they are announced. The heliospheric imagers on STEREO will watch outflows and shocks racing away from the Sun, occasionally with a comet tail in the same field. The Parker Solar Probe will register the plasma and dust environment from within the inner heliosphere. Together, these assets ensure that even ordinary comets become probes of physics that matters to our planet. And so the season's logic is clear. A rare interstellar traveler, 3I/ATLAS, provides a control point that does not share the formation history of our comets. Two brightening home comets, Lemon and SWAN, give photographers and naked eye observers targets with changing structure, fast light curves, and potentially dramatic plasma behavior. 3 additional comets stretch the story into winter, blocking out a continuous thread of activity as the Sun approaches its own peak of magnetic vigor. The planets and their spacecraft supply vantages that Earthbound observers lack when geometry is unkind. The result is not a single headline event, but a weeks-long natural experiment. Watch for green tints from diatomic carbon in the Comet. Watch for the sudden bite of solar windstorms that rip plasma tails free. Watch for the small oscillations in brightness that betray changing rotation and active areas on the nuclei. In a season like this, the night sky is not a fixed dome. It is a living flow, and for once the flow carries 7 messengers at the same time. At perihelion on October 29, 2025, the interstellar visitor 3I/Atlas reaches its point of closest approach to the Sun. This is the stress test moment when the full energy budget of sunlight meets the nucleus. Temperature climbs, buried volatiles find pathways to space, and the fine details of nucleus structure begin to matter. If the object carries a crust that is tough, gas production may ramp up more slowly and remain confined to vents. If the surface is fragile, pressurized pockets can burst through and trigger brief outbursts. The coma thickens with gas and entrained dust. Jets sculpt spirals and fans that betray spin and topography. To observers on Earth, the geometry is frustrating. The comet lies near superior conjunction, tucked close to the Sun from our perspective. But to spacecraft with different vantage points, including platforms placed to study the inner heliosphere, the scene is ideal. Instruments that read ultraviolet light, infrared emission, and scattered sunlight can watch the chemistry of the coma change hour by hour as fresh layers of ice begin to sublimate. For an interstellar comet, composition is the headline. Water ice begins to drive activity as the object moves inside about 3 astronomical units. Carbon dioxide ice can lift dust at distances beyond that. Carbon monoxide ice can fizz even farther out. The ratios among these volatiles act like a fingerprint of the birth environment. A nucleus formed in a very cold region of a distant disk preserves more carbon monoxide. A nucleus assembled closer to a young star carries less. As 3I/Atlas warms toward perihelion, the balance among water, carbon dioxide, carbon monoxide, and a family of nitriles reveals where in its native protoplanetary disk this body likely took shape. The coma's color offers a quick clue. A green hue points to emission from diatomic carbon and a faint glow from the cyanide radical. Those species are not fundamental to the nucleus. They are created in the coma when sunlight breaks larger molecules apart. The relative strengths of these emissions map out the comet's chemistry in real time. Spin state is the next diagnostic. Outgassing produces torque. If jets are offset from the spin axis, or if their strengths are uneven, the nucleus experiences a twist. The rotation period can speed up or slow down by measurable amounts within weeks. A spin axis can precess. In extreme cases, rotation accelerates until weak material fails. That sequence, from jet torque to structural change to fragmentation, has been documented in home system comets. For an interstellar comet, the exact thresholds for failure are unknown. During perihelion, the science teams will examine coma morphology for repeating patterns that line up with a nucleus rotation cycle. A corkscrew plume or a periodically bright arc hints at a jet that rotates into and out of sunlight. Any change in the repeat interval across several days tells us that torque is changing the spin rate. The sign of the change indicates whether the jet thrust points slightly ahead of or behind the subsolar point on the surface. The tail system becomes a simultaneous probe of dust and plasma. A dust tail bends away from the orbit as radiation pressure shoves small grains more strongly than large grains. A plasma tail points almost directly away from the Sun, aligned with the magnetic field carried by the solar wind. Near perihelion, both tails lengthen quickly. If a coronal mass ejection sweeps past, the plasma tail can kink in minutes of time or disconnect entirely, leaving a pale strand that drifts downwind while a new tail regrows from the coma. Intervals of rapid change are especially valuable for interstellar comets because they force a response in the plasma that can be modeled with magneto-hydrodynamic codes. The shape of a kink and the rate at which it travels tell us about the magnetic field strength and the speed of the solar wind at the comet. A disconnection event offers a timestamp for when the magnetic field orientation flipped. If 3I/Atlas experiences such an event near perihelion, the timing will allow researchers to trace the solar disturbance back to its origin on the Sun. At a deeper level, perihelion is when the insoluble properties of the nucleus are revealed. Grain size distribution in the dust controls the brightness of the tail. Thermal inertia in the surface layers sets the delay between peak sunlight and peak outgassing. Porosity controls how gas percolates toward space and whether dust grains are lofted or trapped. All these parameters feed the light curve. Interstellar comets arrive as unknowns. They have no prior apparitions to anchor predictions. For 3I/Atlas, the curve across late October becomes a laboratory for stress testing the assumptions baked into models that observers use every season. A steep rise indicates either fresh volatile exposure or forward scattering that enhances brightness when the phase angle between the Sun, comet, and Earth widens. A plateau suggests that crusty layers are limiting gas flow. A sudden spike may be a localized outburst rather than a global change in activity. The point is to read these signals without sentiment and with an eye toward physics. Geometry matters. The small elongation angle from Earth in late October means light from the comet fights twilight and scattered sunlight. Even with large telescopes, the field remains bright. That is why spacecraft placed away from Earth become crucial. A probe in solar orbit has a different line of sight and can watch the comet in darker sky while we peer through dusk. Instruments that monitor ultraviolet hydrogen emission can detect the vast cloud of atomic hydrogen created when sunlight splits water molecules in the coma. Infrared spectrometers can separate emissions from water, carbon dioxide, carbon monoxide, and other gases. High-cadence imaging can record the rotation phase of jets and track changes in tail structure across a single rotation period. The full picture then emerges from multiple vantage points, one set of eyes near Earth, another set closer to the Sun, and perhaps a third at a planet that happens to lie nearly along the path. Because the visitor comes from outside the solar system, its orbit is hyperbolic. The comet enters once and leaves for good. The approach speed far from the Sun is tens of kilometers per second, a reminder that this object has spent eons of time drifting in interstellar space before the gravity of the Sun deflected it onto a brief sunward arc. The hyperbolic path implies that any non-gravitational acceleration caused by outgassing can be measured cleanly because there is no need to account for small changes accumulated over repeated orbits. In practice, teams fit the position measurements with gravity-only models and then add small thrust terms aligned with or against the Sun. If the fit improves, the thrust is real. For an interstellar comet, these terms are valuable because they quantify how efficiently sunlight is converted into gas flow and gentle thrust. They also show whether jets are systematically brighter on the day side or the night side of the nucleus, which in turn hints at thermal inertia. A final point on the interstellar moment. Perihelion is not a single instant. It is a process that unfolds across days. The comet warms, reacts, and relaxes if the nucleus carries layers of material with different strengths. The sequence of activity may step as one layer gives way and another takes over. Some comets show day-night asymmetry, with outgassing suppressed until the subsolar point has crossed into a region with more volatile ices. Others respond quickly to sunrise on the nucleus. For 3 I/ATLAS, the cadence of change is as important as the peak. The way activity turns on and the way it fades offers a fingerprint of structure as real as a radar map, and all of it is recorded in gas lines and dust motion. Now attention shifts to a comet that is more generous to human eyes. C 2025 A6 Lemmon reaches perihelion on November 8th. The forecasts that matter to observers are simple. Under good dark skies, with no moon in the way and with transparent air, Lemon may crest near the threshold of naked eye visibility around 4th magnitude. That is the level at which a careful observer in a dark rural site can step outside, adapt for a few minutes of time, and then find a faint cotton ball with a short tail in the western evening. In suburban light or under thin haze, the same comet shrinks back into the binocular class. None of that is a failure of the comet. It is a lesson in surface brightness. Comet light is spread across a diffuse coma, and city sky glow erases diffuse features first. Plan for a dark site if you want the textbook experience. Placement in the sky is kind to northern latitudes through the second half of October into early November, with the comet cruising upward in the early evening as it sweeps around the Sun to perihelion. The phase angle can grow toward values where forward scattering lifts the dust tail to greater brightness than simple geometry would suggest. In forward scattering, tiny grains preferentially redirect sunlight into your line of sight when the Sun, comet, and Earth form a nearly straight angle with the comet between. The effect can sharpen the tail and raise its surface brightness. If the geometry aligns just right, the tail can show bright rays and striae, subtle bands that trace size sorting within the dust stream. This is the moment when patience with focusing and exposure time pays off. A stack of short exposures can reveal the fine structure without washing out the inner coma. Expect the inner coma to show a sunward fan where jets carry dust off the nucleus in streams that curve under radiation pressure. A small telescope in the 10 to 15 centimeter class at moderate magnification can separate that sunward fan from the anti-solar tail. Sometimes a parabolic hood appears on the sunward side, a bow shock-like boundary between the solar wind and the ionized gases streaming from the coma. In long exposures, a narrow plasma tail may separate from the dust tail and point almost directly away from the sun. If the solar wind is quiet, the plasma tail is a clean line. If a shock passes by, watch for sudden bends and structure that seems to move down the tail from one night to the next. These changes are not imagination. They are the signature of magnetic pressure and the flow of charged particles through the tail. Brightness estimates will wander. Visual observers grade the central condensation on a 9-step verbal scale from very diffuse to almost stellar, then adjust their magnitude estimates accordingly. Digital photometry uses apertures measured in arc minutes to capture a consistent fraction of the coma light. Both methods are useful and both have biases. If Lemon throws a small outburst, a visual estimate can land brighter than a digital one because the central condensation spikes. If dust production surges but spreads out, a digital aperture may capture more of the new light than the human eye. When you read that, Lemon is 4th magnitude in one report and 5th magnitude in another on the same night. The difference often reflects method more than disagreement. The sodium tail deserves a special look. Some bright comets display a narrow tail of neutral sodium atoms that glows at a yellow color near the sodium D line. Most of the time, it is hidden by the brightness of the dust tail. Under the right conditions and with filters that isolate the sodium emission, the narrow tail emerges. It lies between the dust and plasma tails and behaves in its own way because sodium atoms feel radiation pressure and also ionize on a time scale that competes with their travel time. Photographs of Hale-Bopp and a handful of later comets have shown this elegant addition. Lemon is not guaranteed to display it to small instruments, but photographers with access to narrow-band filters can try. The presence or absence of the sodium tail gives clues about grain composition and sputtering processes at work near the nucleus. Timing the observing run matters. The safest rule is simple. Never point optical gear near the sun. Wait until the sun is well below the horizon. Pick a clean western view with low trees. Plan for the comet to sit low in bright twilight during the first days of its best run. Then climb higher night by night. Use binoculars with a stable support. A parallelogram mount or a tripod with a simple adapter turns a shaky view into a steady one. For a small tracking mount, a short telephoto lens around 100 millimeters of focal length frames the inner tail and the star field. Because skies are often milky near the horizon, take many short exposures and stack them rather than one long exposure. This approach keeps the background uniform and preserves the faint outer tail. As the comet climbs with each passing evening, lengthen your exposures in small steps and compare stacks to see how the tail grows. There is practical science in these pictures. By measuring the ridgeline of the dust tail across several nights, you can see the graceful shift from large grains near the nucleus to smaller grains farther behind. The geometry of that curve follows the logic of synchrones and syndines. an approach that links particle size and time of release to where grains end up. If you draw curves that represent grains of a single size released at different times and curves that represent different sizes released at one time, the crossing of those families of curves explains the pattern you see. For the plasma tail, the story is different. It is a field line tracer. A sudden jog records a change in the interplanetary magnetic field or a density jump in the solar wind. The speed at which a feature drifts down the tail maps to the flow speed. Your backyard time series lines up with spacecraft readings to reconstruct the space weather that shaped the tail overnight. A subtle possibility comes later in the season. Meteor activity sometimes responds to dust that a comet laid down along its orbit weeks or months earlier. If Earth crosses a fresh dust sheet, a mild enhancement in meteor counts can occur. The radiant point may not align with a well-known major shower. Small video cameras that watch the sky all night can catch such an uptick. Even a negative result matters because it constrains how much large dust Lemon actually released near perihelion. The physics of dust size distribution feeds back into models of tail brightness and the long life of the dust trail along the orbit. For a comet that may be bright enough to draw thousands of images, this is a chance to connect pretty pictures with quantitative results. To understand why brightness forecasts wander from optimistic to cautious, step back from the calendar and look at the anatomy of orbits and light curves. At the simplest level, a comet brightens as it approaches the Sun, because sunlight grows stronger, and as it approaches Earth, because distance shortens. Apparent magnitude is therefore tied to two distances: heliocentric distance and geocentric distance. Observers often express the brightness as a sum of a constant that encodes the nucleus and coma plus 5 times the logarithm of the distance from Earth, plus a factor multiplied by the logarithm of the distance from the Sun. The factor is not universal. Dust-dominated comets often brighten faster with decreasing solar distance than gas-dominated comets. The factor can range from about 2 to about 8 in words. When forecasts for Lemon differ, the disagreement frequently rests on what factor to assume. Early in an apparition, when gas production is low and dust dominates, a larger factor can fit the data. Later, as gas lines strengthen, a smaller factor may be more realistic. When we say orbit, we mean a path shaped by gravity and perturbed by jets. Jupiter family comets trace short loops with periods of a handful of years and a Tisserand parameter relative to Jupiter that marks their dynamical class. Halley-type comets carry periods of many decades and often have steeply inclined paths. Long-period comets that come from the Oort cloud stream in on near parabolic arcs and can return after tens of thousands of years. An interstellar comet follows a hyperbola that never closes. The Tisserand parameter gives a quick way to sort orbits by how much Jupiter shapes them. A value near 2 or 3 in words points to strong interactions with Jupiter in the recent past. A very different value marks objects that avoid close approaches. If you imagine a family portrait of comet orbits, Jupiter family members huddle near the plane of the planets. Halley-type comets trace tilted loops. Long-period comets arrive from any direction, and the interstellar visitor cuts across everything once and leaves. The physics that drives activity sits on top of these orbits. Sunlight warms the surface. Heat diffuses downward. Volatiles in the pores of the surface evaporate and find their way to space through cracks and vents. Gas expands and drags dust with it. The elasticity of this coupling depends on grain size, pore structure, and cohesion. Small grains lift easily. Large grains need more gas flux to move. The result is a selection effect. Early in the approach to the Sun, when only very volatile ices are active, mostly small grains escape. As water ice begins to sublimate, the drag increases and larger grains join the flow. The color and polarization of comet light respond to this change. A coma rich in small grains scatters more blue light relative to red and polarizes light differently from a coma with larger grains. Sensitive polarimeters can diagnose this shift. Images alone can hint at it through changing texture in the inner coma. Phase angle adds another layer. When the Sun is behind you and the comet lies in front, the phase angle is small and the coma looks more symmetric. As the angle grows, the dust tail benefits from forward scattering and can brighten more than expected. Some comets show a pronounced surge in brightness near large phase angles, while others only modestly. The difference rests on grain properties. Fluffy aggregates scatter light differently from compact grains. Transparent grains do not behave like opaque ones. In principle, the shape of the phase curve contains information about composition and microstructure. In practice, separating phase effects from changes in gas production is tricky. That is why extended monitoring across a month matters. As the phase angle rises and then falls, and as the comet moves inward and then outward, you can untangle geometry from physics. Non-gravitational acceleration is the most direct sign that jets matter. It shows up in orbit fits as a small extra push directed roughly away from the Sun when activity is strongest. For a comet on a closed orbit, this push produces a small timing shift in the next return. For an interstellar comet, it changes the asymptotic speed by a tiny amount. Observers modeled the thrust with three components, one radial, one transverse, and one normal to the orbit plane, each with its own time dependence that follows the solar distance. A positive radial term means day-side jets dominate. A negative radial term points to night-side activity that persists because heat remains in the subsurface after sunset on the nucleus. If a transverse term stands out, it hints that vents are concentrated away from the sub-solar meridian, or that rotation exposes jets more favorably on one side of the orbit. This is the quiet language of comet geology, written in millimeters per second, squared and decoded with patient tracking. The surface of a nucleus evolves over a single apparition. Sublimation leaves behind lag deposits of dust that can armor the surface. Gas then fights to find new routes to space. When a fissure opens, an active jet switches on, and the coma structure changes within hours. Sunlight can collapse caverns whose roofs were undermined by sublimation, exposing fresh ice. The Rosetta mission at Comet 67P recorded cliff collapses, rolling boulders, and sudden jets that turned on after local sunrise on the nucleus. While images of Lemon and SWAN will not resolve such details directly, the timing of outbursts and the repetition of jet features across rotation cycles will echo the same geology. The interstellar visitor adds a wild card. Its surface has not been reworked by repeated perihelion passages in our system. It may carry more pristine textures or may have been battered by micrometeoroids during its long interstellar cruise. Either way, its response to solar heating tests how universal our models really are. Charge exchange X-ray emission transforms comets into remote diagnostics of the solar wind. Highly charged ions in the wind, such as oxygen or carbon stripped of many electrons, steal electrons from neutral atoms in the coma. The captured electrons drop into lower energy states and emit X-rays. The spectrum of that glow reveals the composition and charge states of the wind at the comet. Because X-ray brightness depends on both gas production and solar wind flux, a coordinated campaign across Lemon, SWAN, and 3I/ATLAS can distinguish local gas effects from wind variability. Imagine 3 detectors placed in different corners of the inner system, each glowing in response to the same storm. The timing and intensity in these 3 locations provide a 3-dimensional view of the disturbance. Dust dynamics has a longer memory. Large grains ejected near perihelion do not wander far from the orbit. They form a dust trail that lingers for years. Over time, that trail spreads and sometimes seeds faint meteor activity when Earth crosses it. Small grains disperse quickly and fade from view. The size distribution is often approximated by a power law, with the number of grains decreasing steeply as size grows. A steeper distribution means light is dominated by small grains and tails appear broader and more diffuse. A shallower distribution places more mass in large grains and produces sharper features. Photometry of the tail at several distances from the nucleus can separate these cases. The way brightness falls off with distance from the nucleus tells you which sizes dominate. In this sense, a tail is not merely a pretty plume, but a laboratory that encodes the microphysics of dust production. There is one more piece that matters for both prediction and interpretation. Thermal inertia controls how quickly the surface responds to changing sunlight. A surface with low thermal inertia heats and cools rapidly. Activity turns on soon after local sunrise on the nucleus and fades soon after sunset. A surface with higher thermal inertia responds more slowly. Activity peaks some hours after local noon on the nucleus and persists into the night side. This delay shows up in light curves as an asymmetry around perihelion. Some comets are brighter on the outbound leg than on the inbound leg at the same solar distance because heat stored in the subsurface continues to drive gas after perihelion. Others show the reverse. When you see a prediction that a comet will keep brightening even as it moves away from the sun, you are reading an assumption about thermal inertia and the depth of volatile layers. Bring the pieces back to the practical season. 3 I/ATLAS tests models of chemistry and thrust under difficult viewing geometry. Lemon offers a realistic chance for a bare eye glimpse and a first-class target for binoculars and small telescopes. The surge in activity near Lemon's perihelion will give photographers a chance to catch rays and striae and perhaps a slender plasma tail with a gentle kink if the solar wind cooperates. The interstellar visitor may hide in twilight for most of us, yet still rewrite pages in the handbook of comet composition. The 2 comets operate in tandem. One delivers spectacle. The other delivers a benchmark. Together they give the National Aeronautics and Space Administration and the broader community an unusual data set, a rare interstellar chemistry experiment and a nearby dust and plasma workshop unfolding almost at the same time. As you prepare, calibrate expectations with 3 simple rules that fold all this anatomy into watching plans. First, Brightness is not a promise. Treat every forecast as a range. Look for trends more than single reports. Second, geometry is destiny. If the elongation is small, expect a fight with twilight and use instruments or spacecraft data as your main window until the comet pulls away. If the phase angle grows, be ready for forward scattering to sharpen the tail. Third, details matter. Record times in universal time if you can, note sky transparency, and write down the degree of condensation in words. Those details make your contribution useful to others and help you compare your results from night to night. From perihelion physics to tail kinks, from dust grain sizes to non-gravitational pushes, the anatomy of orbits and light curves explains why this season is more than a countdown of dates. It is a coherent opportunity to watch how sunlight negotiates with ice and dust and gas, how magnetic fields carve and reconnect, and how a visitor from interstellar space responds to a star it has never seen before. The calendar stakes are clear. Late October brings the moment of truth for the interstellar comet. Early November brings the practical peak for Lemon. Understanding what you are seeing turns the spectacle into knowledge. Dust sets the scene and plasma writes the plot. A comet begins as a dark nucleus with pockets of ice and trapped gases. Sunlight warms the surface, ice turns to gas and drags dust into space. The result is a coma, a roughly spherical cloud where molecules collide and sunlight pushes electrons off atoms and molecules. Inside this cloud is a pressure balance. Gas flows out, the solar wind flows in, and a small electromagnetic world takes shape. Two large-scale tails then emerge together. The dust tail is curved and pale, shaped by sunlight itself, which pushes the smallest grains hardest and lets the big grains lag behind only slightly. The plasma tail is narrow and straight. It points almost directly away from the sun because the charged particles in it are guided by the interplanetary magnetic field that streams with the solar wind. The dust side begins with texture. Jets from the nucleus feed dust into preferred directions. Rotation turns these jets into fans and arcs. The smallest grains scatter bluer light more readily than the largest grains, so color and polarization change as the grain population evolves. When outgassing surges after sunrise on the nucleus, more large grains lift free. The inner coma becomes rough and clumpy as sunlight sweeps across slopes and cliffs. Photographs sometimes show delicate bands called striae in the dust tail. These bands are a record of size sorting, where the smallest grains drift faster away from the nucleus under radiation pressure and leave behind braided sheets of larger grains. If you follow the curves back toward the head of the comet, you can often infer when a given sheet of dust was launched. Dust also hides a third tail that many observers never see. A few bright comets grow a narrow sodium tail that glows with the golden color of sodium in sunlight. It lies between the dust and the plasma tails. Sodium atoms are knocked from grains by sunlight and by tiny collisions. They feel sunlight strongly and fly away quickly. With a narrow filter, this elegant thread can stand apart from the broader dust plume. In most apparitions, it remains subtle and requires experience to record. Yet, when it appears, it adds a chemical signature that connects the nucleus to the light we see. The plasma story runs by different rules. Gas leaving the coma becomes a stream of neutral molecules. Sunlight breaks those molecules into atoms and ions. The newborn ions are picked up by the solar wind. At that instant, they feel the magnetic field carried by the wind and begin to circle that field while being carried away. The circling begins as a ring beam, then spreads into a flow that lines up with the magnetic field. The result is a plasma tail that is sensitive to the direction and strength of the interplanetary magnetic field and to the speed and pressure of the solar wind. Imagine a windsock on a mountain ridge. It tracks gusts and shifts, and so does the ion tail of a comet. The comet carves a miniature magnetosphere. Closest to the nucleus, gas flows out mostly unhindered. Farther out, ions pile up and the magnetic field drapes around the coma. There is often a sharp transition where the solar wind slows and is diverted. Spacecraft have crossed this frontier at several comets and found an induced magnetotail that resembles a planetary magnetotail. Yet it is created not by a permanent internal field, but by the flow of the solar wind around an obstacle made of ionized gas. Deep inside, missions have measured a place with almost no magnetic field at all, a diamagnetic cavity where dense neutral gas and strong currents push the field away. The European Space Agency missions to Halley and to the comet studied by the Rosetta spacecraft both found evidence for this cavity. In the narrow band between the cavity and the draped field, currents run and waves ripple. It is a layered world, and every layer changes as the sun's wind changes. Storms in the solar wind add drama. When a coronal mass ejection races outward, it carries a twisted magnetic field. If that field rotates quickly as it sweeps past a comet, the ion tail can detach in a disconnection event. The old tail peels away and drifts downwind. A new tail grows almost immediately from the coma and points along the new field direction. Time-lapse imaging has recorded this drama. The key diagnostic is a sudden gap followed by a fresh, straight, bright tail segment. If you watch over an hour of time, the gap widens as the old material moves away. Physically, the driver is magnetic reconnection in the flow past the comet, a process that rearranges field lines and releases energy. The same physics unfolds in planetary magnetotails and in solar flares scaled to the small laboratory of a comet. Not every disturbance cuts the tail. Sometimes the field swings less violently or pressure rises gently. Then the ion tail shows kinks, gentle steps, or a traveling wave. A bright knot can slide away from the nucleus, keeping a fixed separation angle from the sun as it recedes. That knot is not a bullet of matter. It is a pattern in the plasma flow, a signal that a compression passed through, or that the field direction changed piece by piece. The speed of the feature helps infer the speed of the solar wind at the comet. If two comets in very different parts of the inner system show changes within the same day of time, the comparison sketches a three-dimensional picture of the disturbance as it spreads. Subtle microphysics appears in the light. Charge exchange between heavy ions in the solar wind and neutral atoms in the coma produces soft X-rays. That glow is faint and requires space telescopes to detect. Its presence tells us the composition and the charge state of the wind where the comet resides. Radio emissions have been seen from plasma waves excited when the solar wind meets the comet. These emissions arise when pickup ions disturb the flow and set up oscillations. While you will not hear them with a backyard receiver, they are part of the same physics that imprints kinks and scallops onto the visible tail. The tail system is therefore an instrument. The dust tail integrates behavior over hours of time, encoding grain sizes and the vigor of gas flow. The plasma tail plays like an oscilloscope trace for the solar wind, reacting within minutes to sudden changes and redrawing itself as the field rotates. During the approaching season, with the interstellar visitor near the Sun and the home system comets placed for easier viewing, the sky becomes a multi-probe experiment. One comet supplies plasma diagnostics. Another supplies texture and brightness patterns in dust. Together, they let observers read both the short-term weather of the solar wind and the long-term health of the nucleus. Turn now from physics to practice. The best plan begins with location. Choose a site with a dark western or eastern horizon, depending on the evening or morning window. City light scatters most strongly near the horizon, so even a short drive can transform a disappointing faint smear into a rewarding scene with structure. Arrive early. Give your eyes 20 minutes of time to adapt. Use a red light that is dim enough to preserve night vision. Shield phone screens. A folded sheet with a simple finder chart printed in large letters beats a bright screen when you are near twilight. Equipment matches goals. For a first look, a good binocular is the most flexible tool. A 7 by 50 or a 10 by 50 class binocular gives a bright field and enough magnification to separate the coma from nearby stars. Brace your elbows or use a simple tripod adapter so that fine structure does not smear in a shaking view. A small refractor around 10 to 15 centimeters in aperture on a stable mount makes the inner coma come alive. Use moderate magnification to darken the sky and to bring out jets and the sunward fan. A larger Dobsonian-style reflector will show more tail length, but in bright twilight, a small high-quality refractor can achieve splendid contrast. Cameras expand what you can see. For a static tripod, use a bright wide lens and take many short exposures. 10 to 30 seconds for each frame is a helpful range, but adjust to your sky. Stack the frames later to build faint detail. If you have a tracking mount, try a short telephoto lens in the 100 to 200 millimeter range to frame the tail without blurring stars. Keep your lens clean. Dew and thin haze near the horizon can lower contrast. A simple dew strap or a breath of warm air and a soft cloth can rescue a session. Use raw image format if your camera allows it. That preserves faint gradients in the tail that a compressed format can flatten away. Calibrations improve results more than brand names. Take dark frames of the same duration and temperature as your light frames. Take flat field frames by pointing at an evenly illuminated surface and recording a short exposure to map dust shadows and vignetting. Take zero exposure frames to capture electronic offsets. Calibrate, register, and then stack. When you stretch the result carefully, you will find that the outer dust tail extends farther than you thought, and that the plasma tail reveals a clean central spine. If a kink or a faint disconnection appears, annotate your image with the time and note the angular distance of the feature from the head. Those numbers make the picture useful to others. A few habits separate a hurried look from a confident record. First, write down times in universal time and include your location. Second, estimate the degree of condensation using plain words from very diffuse to almost stellar, and record the apparent diameter of the coma in arc minutes by comparison with known star separations. Third, note transparency and seeing. Haze can change tail visibility more than any other factor. Fourth, learn to use averted vision and slow panning. A gentle sweep often reveals the direction and length of the tail more effectively than a fixed stare. Safety is non-negotiable. When a comet sits near the sun in the sky, the temptation is to search low in bright twilight. Never aim binoculars or a telescope anywhere near the sun. Wait for the solar disk to be well below the horizon. If the inner planet appears in the same area of sky, treat that proximity as a warning that the sun is not far away. For daytime experiments, rely on space-based coronagraph images rather than your own optics. No image is worth an eye injury. At night, guard against dew and cold. Warm batteries in a pocket. Use a tripod that will not blow over. Sweep the area for trip hazards before dark. Maps help. The comet path shifts by a noticeable amount from one night to the next. A planetarium program or a paper chart with plotted positions for several dates will keep you on target. Learn a handful of anchor stars along the path. For example, bright stars in Virgo and Libra mark waypoints for many evening apparitions in northern autumn. Practice star hopping in daylight on a chart so that your eyes can stay on the sky at night. Remember that a comet does not move much within a single short session. If what you see slides fast across the field, you may be tracking a satellite or an aircraft. Take your time and let the field settle. Astrophotography offers a bonus experiment. With a tracking mount, take a series of images guided on the comet rather than on the stars. That keeps the coma centered and reveals the structure of jets near the nucleus. Then stack a second sequence guided on the stars. That preserves the background field. Comparing the two shows how far the comet moved and whether the inner structure changed during your session. If a jet rotates into view as the nucleus spins, you may catch a change in the sunward fan within an hour. That is satisfying evidence that you are seeing a living object rather than a fixed smear. Reporting closes the loop. The International Comet Quarterly and the Comet Observation Database both welcome well-documented observations. A short note with the time, site, instrument, estimated magnitude, coma size, and a brief description of tail structure adds to the world's record. If you captured a suspected disconnection or a strong kink, share your data with heliophysics groups that model the solar wind. Amateur time series with minute-by-minute cadence can help locate the arrival time of a shock in a way that complements spacecraft readings. In this way, a backyard session turns into a data point in a solar system scale experiment. All of this observing effort meets a larger question. What does a season of multiple comets mean for the Sun and for space weather? The short answer is that comets do not drive the solar cycle. They do not trigger global solar storms. The Sun sets the rhythm. Yet comets can influence local plasma conditions and concede small-scale effects. Sun-grazing fragments that skim the outer solar atmosphere can excite brief jets in coronagraph images. Outflowing gas from a bright comet adds pickup ions to the solar wind. This process called mass loading can slow the flow and can change how waves propagate near the comet. The effect is local, measurable at the comet and a short distance downstream, and it fades with distance. It does not change the overall behavior of the solar wind on a global scale. The value of a comet surge is therefore diagnostic. Several comets placed at different longitudes and latitudes in the inner system act as moving probes. If a coronal mass ejection erupts, its arrival time at each comet can be measured by watching for tail kinks or disconnections. Those arrival times, combined with direct readings from spacecraft near Earth and near Mars, trace the shape and speed of the disturbance in 3 dimensions. When the interstellar visitor is near the Sun and a brighter home comet is well placed for Earthbound observers, the pair becomes especially useful. One records composition and dust physics in detail. The other annotates the space weather with visible changes that even small telescopes can follow. A second benefit is statistical. When many comets are observed in a short span of time under similar solar conditions, differences among them stand out. One may show frequent small outbursts, another may remain steady, one may show a sharp plasma tail that responds quickly to solar wind shifts. Another may show a soft, diffuse tail that suggests lower ion production. These contrasts sharpen our models of nuclear strength, volatile layering, and the way jets impose torque. If several comets display sodium tails, the comparison across dates and phase angles tells us about grain sources and erosion processes that are usually hidden in single object studies. The third benefit is public readiness. Tail disconnections and strong tail kinks are vivid. When such features appear during an interval of active solar weather, they offer a teachable moment. Broadcasters can show a comet photograph and link it to auroral alerts. Satellite operators can match visible changes to sensor readings, and citizens can understand why space weather forecasts matter. The comets become the most intuitive visualization of plasma dynamics that exists in nature. A glowing strand detaches and floats away. Even without technical terms, the meaning is clear. The space around us is not empty. It is a river that sometimes floods. This season also encourages a habit of disciplined skepticism. Forecasts of brightness are not promises. Predictions of dramatic plasma behavior are not guarantees. The responsible stance is to expect a range of outcomes and to observe carefully. If Lemon surges to naked eye visibility for only a few days of time, that is still a success. If the interstellar visitor remains faint to ground-based observers, that is not a failure. It is a call to spacecraft and to careful spectroscopy. The science is robust either way. Comets do not owe us a show. They offer a laboratory, and the best laboratories are those that challenge assumptions. Staying current is simple. The National Aeronautics and Space Administration and the European Space Agency both publish regular summaries from their heliophysics missions. The Minor Planet Center provides updated positions and brightness estimates. The Space Weather Prediction Center in the United States keeps a daily and hourly watch on the sun's behavior and on disturbances that may reach Earth. Observatories and experienced amateur networks post finder charts and observing windows as geometry evolves. Check these sources as the dates approach so that your plan reflects the latest orbit refinements and brightness trends. Adjust your route to a dark site if needed. Adjust your equipment plan if the comet brightens or fades beyond expectations. The arc of the story is clear. Dust creates the beauty and the baseline physics. Plasma adds the fast drama and the link to the sun. Observers on the ground write the daily log, while spacecraft fill in the parts hidden by geometry. A rare interstellar visitor crosses paths in time with brighter local comets. The sun moves toward and through a period of energetic behavior. For several weeks of time, the solar system will host a connected experiment. Each clear evening or morning gives you a page of data and a view into the way light, gas, and magnetic fields negotiate with gravity. Use the next clear night to practice with the sky near the western horizon. Learn your camera at high sensitivity without blowing out the inner coma. Try a star field you know well and measure how long a single frame can run before stars blur on a static tripod. Check your dew prevention. Verify that you can annotate times and directions without staring into a screen. Pack warm layers for yourself and a lens warmer for your optics. When the comets arrive and the sun decides to flex, you will be ready to record clean arcs of dust, straight spines of plasma, and perhaps the sudden parting of a tail that marks the invisible touch of a storm.